for coming. So today we are very pleased to have Professor Tae-Young Yoon from KAIST. He's at the Graduate School of AI.
Yeah.
And his department is moving to Seoul pretty soon. So this is going to be the last talk we give in Daejeon. Pretty good. And talk about some regrets.
Right, yes. Right. Okay, good afternoon everyone, and thank you for inviting me here, Davin and Professor Sang-il. So today I'm gonna present my very recent work, Regret in Online Recommendation Systems, which was presented at NeurIPS 2020. So NeurIPS is a prestigious conference for machine learning and artificial intelligence technique. Today I select this paper because this work is very related to discrete math, and I'm presenting here. So this work is joint work with Kaito, Nare, and Alexandru. And so in this work I will explain how to make pairs between item and users to have a better happiness of users. Yes, so this is introduction. So the goal of today's talk is, and this paper is, to maximize the expected number of successful recommendations. So here, the successful recommendation means at each time a user arrives to the system, and the system has a bunch of items. Like if you consider Netflix system, Netflix has a bunch of movie or TV shows. And when a new user arrives to the system or connect to the Netflix system, the Netflix have to recommend a list of movies to each user. Okay, so here we consider very simple model as a starting point. So at each time, the system can recommend at most one item, and user just can respond positive or negative. User can click I like this movie, or user click I dislike this movie. Okay. And of course, the goal of the system designer is we want to maximize the number of positive responses from the sequence of observations. So based on sequence of observation, we want to maximize the future positive reward, future positive responses. And so to do so, we have to really carefully design the sequence of recommendation, because we have to acquire some information on items and users. After that, we can recommend a good movie to good user. Okay. To design a recommendation algorithm which can suggest a likable movie to every arriving users. So this is mathematical problem setting. So there are n users. So I use the notation n to denote items. There are n items, and there are m users. So I use capital M, the character m to denote the number of users. And at each time t, a user is chosen uniformly at random among m users. Okay? And the algorithm recommends an item to the user, not multiple items, just one single item to user. And the user responds to the recommendation. User likes the recommended item with an unknown probability low IU. So here I is item index and U is user index. Okay, so there is some hidden parameters the system don't know and user also doesn't know. We have to learn such parameters so that we can give a nice recommendation. So we have to find the user and item pair that has high low IU value. Then we can expect high positive response. If we recommend an item to user having very low IU value, then with very high probability the response is negative. So we have to learn low IU very quickly and then recommend item so that the future responses become very positive rather than negative. Right. And we also consider a null repetition constraint. So this is very hard constraint. So the algorithm does not recommend an item to an item twice to the same user. So if, for instance, if Netflix recommend a matrix movie to one single user. Although the user arrive again, then the system cannot recommend the same matrix movie to the user because he already responds to the matrix movie. Okay, so this is a very strong constraint, no repetition constraint we consider.
If you want to round the probability row IU, but if you just have one observation.
So if we have just one observation, it is impossible to know row IU. So we have to assume that there is some structure, like a row rank structure or very smooth structure. Or we have to assume something for the row IU structure. So I will explain what we assume here.
Items can be correlated.
So items can be correlated, or users share the same preferences, or there is some clusters of users and there are some cluster of items. If we can find the hidden cluster of users and hidden cluster of items based on the clusters, we can give very nice recommendation.
Because by the way, on Netflix and YouTube, repeated viewing is very common.
Yeah. I'm afraid that's just a suggestion. That was also one comment from reviewer. So
Children's content.
Yeah, we agree. So at this moment, we assume no repetition constraint for our mathematical analysis, but yeah, it's very good direction to relax such a constraint. Like we can recommend the same item with some probability, or there is some Markov process. We can forget some past recommendation history and so on. There are many possible directions to relax this no repetition constraint. But at this moment, this is just a starting point. So this is just a starting point to make a mathematical result for recommendation system. So yeah, just please understand our constraint. But yeah, that is very critical concern from our reviewers as well. Yeah, very, very good question. So in this paper, we consider three different models, model A, B, and C, and model A and B is very simple. So today I will focus on model C. Okay. So what is model A and B? So in model A, we assume that there is clustered items. So when items belong to the same cluster, then they will share the same preference. And statistically identical users, so we don't need to discriminate users. All users share the same preferences, and there are hidden item clusters. So whenever we can find the hidden clusters of items and the hidden parameter of each cluster, then as soon as we extract such information, we can give very nice recommendation, right? Because we can classify item here and item here. If row 1U always 0.7, if row 2U from here is always 0.4, the best strategy is always recommend the item belong to this cluster, right? So that is very simple, and the algorithm is very simple, and the analysis is also very simple. So not very interesting model, but as a exercise question, we start with model A, and model B is a little bit more complicated. Sorry?
The classes of items are given.
Classes of items are given but hidden to the system. We have to extract the hidden clusters of items from the observation. So we have to spend a first few random observations to extract the hidden cluster of items. After that, from this information, we can recommend a very nice way. Model B is a little bit more relaxed. There is unclustered items, but still statistically identical users. So all users share the same preference. But items, there's no cluster, but they have some different row IU value, which comes from some random distribution. Okay. So again, row IU depend only on the item, and we can remove the user dependent subscript. So there is row I, the preference of item I, and which is drawn according to some distribution, which is not known to the system. And we say that on item I is within the epsilon best item if the row I is greater than or equal to mu 1 minus epsilon. So here mu 1 minus epsilon is 1 minus epsilon quantile part. So if row I is bigger than mu 1 minus epsilon, then the expected positive reward of item I is a top epsilon portion. And we want to maximize the number of recommendations having this property, and that was model B's analysis. It is still very simple because there is no difference between users. Because every user having identical preferences, we just use some random observation for a few iterations, and then find some estimated row I value, and after that we can build a very nice recommendation algorithm based on row hat I, which is just empirical average of the positive response from some given user. So model A and B not interesting, but they are just exercise problems.
So if you only have one cluster in model A, then is it same as model B?
If we have only one cluster, then there's nothing to learn because every item have the same value. So here in model A, we assume that items belong to the same cluster, they share the same row parameter. Yes. So in model A, if there's only one cluster, then nothing to learn. Any recommendation algorithm will have the same expected positive return.
Or maybe if the number of clusters is equal to number of items, then it's model B?
Yeah, that's true. If the number of clusters is equal to the number of items, then every cluster have one single users, and that is exactly the model B. And in model B, in that case, we cannot recommend the best item all the time because we cannot find the best item among m different items within a finite time because there are a lot of items we assume. Okay. Anyway, model A and B is not such interesting. So we propose model C. So that is the main topic of today's talk. So in model C, there are clustered items and there are clustered users. So items are classified into K clusters. So there are K class of users, and there are L classes of items. So I denote by I1 to I capital K to denote the class of items, and U1 to UL to denote the class of users. And the preference parameter rho IU just depends on the user class index and item class index. Okay, so there is parameter PKL. So here PKL value just depends on the user class index and item class index. Okay, so which means if the two items belong to the same clusters and two users belong to the same cluster, then any pair between them will share the same parameter. Okay, so there is some PKL and which just depends on the class index, item index, and user class index. And then we define regret here. So the regret means how much you can lose when we learn the algorithm when we compare to the best algorithm. So what is the best algorithm? The best algorithm know the hidden cluster and hidden parameter, which is impossible in practice, but let's assume some Gini-aided system exists there, and the system know what is hidden clusters between users and items and the exact parameter PKL values, then the system definitely will recommend the item having the largest PKL value. So if user belong to U1 right to the system, then we will compare all the value from P11 to P1K. Oh, sorry. Yes. and then pick the largest one. So pick the largest one, and then recommend the item belongs to the largest to the cluster having the largest PK1 value, right? So if we know the true hidden clusters of items and true hidden cluster of users, then the system can achieve this amount of positive response. So that is our reference performance. And we want to minimize this regret. So we want to increase this part, our true realization of the positive responses. Okay, so we want to design very nice sequence of recommendations so that this cost becomes maximized. And in other words, we want to minimize this regret. So we lose very tiny amount of value compared to the best algorithm having some Gini-aided system information. Okay. So is it clear the model setting?
There is one question in chat.
Okay.
So for A and B, is it sufficient to observe only one user?
For A and B, is it sufficient to observe?
Only one user because they are
So
from the same distribution.
yeah, good question. But I want to highlight these parts again. So users arrive to the system uniformly and random. At each time, just only one single user arrives to the system, and the user is randomly selected from among the M users. Okay, we cannot choose who arrives to the system. So the arriving user is just randomly selected. And then we recommend just one item to the user, and then the user will leave the system.
So the no repetition condition makes it like different than the what?
So the user can revisit the system after that. Yes.
Then you cannot
Yeah.
I'm getting curious, what can be relaxed more from your settings to mimic the actual recommendation system?
So here, still there are many assumptions. Even in model C, we assume that there are clusters, item, and cluster users, and all items belong to the same cluster. We share the same preference. All users belong to the same cluster, also share the same preference. But that is very strong assumption. So we have to relax. So how can we relax? Maybe we can introduce some latent variable, finite latent dimension, and then we can design some preference matrix as a row rank structure. That is one possible extension, and we are trying to clarify how can we extend this result to the row rank structure assumption. So that is one direction. And also another direction is here we assume that all the observations is independent. So when a user arrives to the system, we just recommend one item at each, and then the next time another user arrives to the system, and we recommend another item. And all the random values are independent as well. But in many recommendation systems, there is some sequence of observation, right? So when user arrives to the system, the user just usually the user can watch several video clips sequentially, and the sequence of watching history can be correlated. So we have to introduce some Markovian model to consider such behavior, and so we also trying to extend this result to Markovian observation and row rank structure, the preference matrix. So actually, this recommendation can be studied with bipartite graph. So this is essentially a bipartite graph. There is item node and there are users node, and one recommendation is connecting line, but with some labels, because after recommendation we observe positive or negative responses. So after a sequence of observation, we can build a bipartite graph where items making nodes and users also making nodes, and the history, our recommendation make a line, edges, and positive or negative responses make some labels to each line. So each line will have information 0 or 1 or -1 or 1, depending on which was positive or negative. So this is just a bipartite graph, and from the bipartite graph with labels, we want to find hidden clusters from the edges and the labels on the edge. Okay. And here we are designing a recommendation system, and every time user arrives to the system, or randomly selected user arrives to the system, and we recommend one of the items to the user. But here we have to consider this. We are trying to minimize the regret. So we have to consider the future outcomes, not just one single time, not just current time, but we also consider future 100 time after or 1,000 time after. So we have to very carefully design the sequence of edges where we want to get more information and where we can expect more high probability positive response. Okay. So at each time, a user, each 0 or 1 label is a random outcome, and random is kind of a Bernoulli random variable with hidden parameter Pij, and Pij just depends on user cluster index and item cluster index. So in this case, the 1 is with probability P11, and in this case, because item cluster 2 and user cluster 1 pair, so with probability P21, so this is P22, and so we have this bipartite graph with the label. And at each time, a user arrives to the system, and then we have to decide which edge we want to connect. So to do that, we have to carefully consider where we have to get more information, where we can expect high positive response probability, so that we can minimize the regret. So which edge we have to choose. This is the system have to decide at every time. So there are many related works. So this problem is very related to multi-armed bandit problem. And what is multi-armed bandit problem? Multi-armed bandit problem, basically there are k actions and a single learner. And at each time t, the learner play an action and get a reward, get a random reward. And each action has its own reward distribution. And the learner should find the best action of which reward distribution has the largest mean reward. So that is a multi-armed bandit problem, and it has a very rich history, and a lot of papers are published and publishing every year. Especially nowadays, every day a new multi-armed bandit paper uploaded to archive. So it's a very crazy area as well, this also. And when you are very interested in this type of work, I recommend to go to a conference called. So there are a lot of multi-armed bandit papers published and published. There are huge number of papers. And more related works are structured bandit problem, mostly linear reward structure. So here they kind of consider the low rank structure response model. So where the hidden parameter having some low rank structure, when you build a matrix, columns comes from items and rows comes from users, then we can build a matrix, and of which elements are the positive response probability values. Then this matrix has structure with low rank. So a structured bandit problem, they basically consider each items and user having some finite dimensional latent variable, and the expected returns can be represented by some inner product between the latent variable, corresponding latent variable. And then the hidden parameter is exactly the low rank matrix, And from the row rank structure, we can design some nice Bandit problem. But usually they do not assume no repetition constraint. Then what is the problem when we don't have no repetition constraint? Then usually the algorithm just exploit one single users on one single items all the time. So that makes some very unrealistic algorithm. But here, because we consider no repetition constraint, we can at least observe some very diverse recommendation and very diverse responses. So that's why we introduce no repetition constraint for our model. And there are also some clustered bandit setting. Again, there are also we done almost every clustered bandit paper also do not consider no repetition constraint. So the algorithm usually exploits just one single item all the time. So very unrealistic algorithm comes out from that paper. So that's why we introduced no repetition constraint and we built our model and algorithm. So this is our result for model C for lower bound. So the lower bound means any algorithm for model C cannot be better than this lower bound. So even if you study this problem 100 years or all your lifetime, you cannot beat this regret lower bound. So this is theoretically shown. So what is the? It looks like very complicated. So where is this bound? Sorry? M was number of items. M was number of users. Yes. Yeah. M was number of users, and N was number of items. So here, so the regret has a 3 term. RNR and RIC and RUC. And when you look at these 3 terms, so the regret proportional to T over M and also proportional to delta. So here delta is the difference between the best cluster expected return and the second best expected return. Okay. So the RNR is T over M times delta, and RIC T over M times 1 over delta, and RUC is just M over delta. So where is why each bound we need? I'll explain one by one. So the lower bound proof is this: each item has to be sampled several times to identify each class members. Otherwise, we cannot know each item belongs to which class. So to understand each item's behavior, we have to spend several samples. We have to waste several samples to understand the item. So which will introduce the regret. Okay? And each user also has to use several samples to identify her or his class members. Okay? So each user and each item have to spend several samples to identify their class index. So that will incur some regret, right? So that is the key component to show a regret lower bound.
You assume that the number of clusters are constant?
Yeah, we assume the number of clusters are constant. So yeah, that's very nice question. So basically, if we don't assume the number of clusters is constant, then the regret should be proportional to the number of clusters. Okay, so that also very tricky part, right? If the number of clusters is very high, then with some chance we cannot choose any items by random selection, right?
Users belong to only a single.
All right. Very great question. Users belong to only single clusters. So in this paper, we consider disjoint membership assumption. But some papers, not this problem, but just a clustering problem, some papers assume some overlapping clusters as well. So we also think we can easily extend this result to overlapping cluster. Yes.
What about the items it's fixed, so new items cannot.
Also, items are fixed. So there are n fixed items, and there is no arrival and no departure. So that's also very great question. So yeah, that's also very interesting direction. What if there is a new arrivals and some departures?
Data mining setting usually build embedding for each item and user beforehand and fine tune based on those interactions. How do you think of that?
So in this paper, we consider at the beginning we have some cold start. There's no information, nothing is given to us. We have to learn from the beginning, from the zero information.
Built according to the edges structure in bipartite graph.
Yes. So from zero information, we have to build a sequence of observations so that we can easily extract the hidden clusters from the zero information. But yeah, so very good if we have some information at the beginning, then we can utilize them, and we can more easily classify items and users, and we can reduce the regret, and we can increase the expected returns. That's true. But here, for mathematical proof, we consider the cold start with zero information at the beginning, and we have to design some very nice initial phase algorithm as well. Right. So to show row bound, so these two is the key idea. Each item has to be sampled several times, and each user also have to sample several times. Then what is the rigorous several times means? We have to show for this row bound proof. And then, so how many samples do we need to use to correctly classify item? From this question, we obtain this row bound. And how many samples do we need to use to correctly classify item? For this question, we obtain this row bound. So, and then all three components are required to classify items and classify users. And based on these three components, we can build a regret row bound. More rigorous proof and all the detailed steps I will skip because we have very limited time. But if you have any question, then very welcome after this talk. Yeah.
I guess you're assuming that the t number of time horizon is at least m times log m, right?
Yes.
The lower bound is increase when m increases.
Yeah, lower bound will increase as yes. So to this row bound, we use a trivial regret row bound. The trivial regret row bound is because of the no repetition constraint. The number of items selected by the system should be greater than the number of arrivals of any user. Because of the non-repetition constraint, when a single user arrives to the system 1,000 times, then 1,000 items have to be recommended at least one time. And the first recommendation of each item has some probability to be bad. So the number of arrivals of any user is correlated to the regret row bound. So we use this trivial regret row bound for the regret row bound analysis. And since the items cluster index is not given at the beginning, the first play must be random guessing, and from that this row bound appear. And the remaining two terms comes from this paper, Sebastian Bubeck and Perchet and Philippe Rigolet, published at COLT 2013. And this paper is about multi-arm Bandit problem when there is side information. What is the side information is we know hidden parameters without indexing. For instance, if there are 3 arms, we have value 0.5, 0.3, 0.1, for example. But we don't know which arm having value 0.5, which arm having value 0.3, which arm having value 0.1. Why we consider this model is related to our work? Because of existence of other items and users having same preference, based on this, we can more easily obtain hidden parameter band, right? So the difficulty to learn hidden parameters becomes more easier when we utilize the other users and other items observations. So we connect our program to this very special multi-armed bandit setting, and then we just bring their row bound to our setting. Then we have the remaining two terms beside the trivial row bound. So to our program, we have this LIC and IC. So the row bound is not such interesting. We just use existing result and trivial row bound. The most exciting part will be the algorithm. And this is algorithm pseudocode, and it is very, very complicated. To make a rigorous proof, we cannot make very simple and intuitive algorithm, but our algorithm consists of several steps and very complicated. But the key idea is quite simple. At first, we use first few budget to extract hidden item cluster using some spectral algorithm. And then we utilize item clusters to identify user clusters. And then from item clusters and user clusters, we give very nice recommendations. So it consists of kind of 3 steps. So this is the informal result, and the results say our algorithm can achieve almost the same regret bound as the row bound. So the row bound is the fundamental limit, and our algorithm achieves almost the fundamental limit, which means our algorithm is kind of optimal. Okay. So you can design a better algorithm than our algorithm, but your improvement just be just a constant factor at most. Okay. So what is the algorithm? The algorithm. Okay. The algorithm first uses random sampling and spectral analysis. So, okay, so I think this is my old version, but yeah, it's okay. Yeah. So the first step is uniform random sampling and spectral analysis. So with some finite budget, at each time we randomly select one of n items. Okay, and then construct an adjacency matrix where only positive responses make edgy for the bipartite graph. So ignore all the negative responses, just keep the positive responses, then the result is just a bipartite graph, right? There's no label on the edge. So because we erase all the negative responses. And because we randomly select each items, the structure can be easily obtained from the adjacency matrix and the graph. The expectation of adjacency matrix will have structure information. Okay. So the question is, does the random adjacency matrix have the structure information despite of the random observation noise? Okay. So what is the mean is, when you take the expectation for the adjacency matrix, so here the adjacency matrix, I will use this is for users, this is for items. The expectation matrix will have some structure like this, right? If these items belong to the same cluster, and these items belong to the same cluster, and these users belong to the same cluster, these users belong to the same cluster, the expected adjacency matrix will have structure. This value will be the same, and this value will be the same, and this value also will be the same, right? And which means your expected adjacency matrix has row rank structure, and the columns and rows tell us the cluster membership. When we can find this expected matrix, from that we can immediately understand the hidden structure of users and items. So that's why many spectral methods are utilized for find the hidden cluster from graph structure, because the expected matrix tell us hidden structure. But the problem is we do not observe the expected matrix, but we observe random realization. So each element will be 0 or 1, and 1 with probability something value here, and with probability something value here, with probability something value here. So we have to reconstruct this expected matrix from this random adjacency matrix. But unfortunately, in many cases, the simple spectral method failed. So when we analyze the eigenvalue of this adjacency matrix, when the problem is easy, the eigenvalue is concentrated around here with some circle shape, and the density of eigenvalue are concentrated here with circle shape, and few big eigenvalues locate some isolated from this dense area. When we have such eigenvalue structure, these very big eigenvalues and corresponding eigenvectors tell us a hidden structure. Then the problem is very easy. So there is some parameter regime. When we have some sufficient number of samples, then such sufficient number of samples make this random matrix having this eigenvalue structure. Then we can easily extract this structure from row rank approximation. Okay, just keep the eigenvalue and the corresponding eigenvectors, and erasing all this part. Basically, all these parts comes from randomness of this adjacency matrix. So when you erase all this part, basically these two eigenvalues and eigenvector tell us almost this structure, and from that we can extract the hidden structure. That is spectral method. When your adjacency matrix have this eigenvalue structure. If this matrix is symmetric, if this matrix is not symmetric, we can draw similar shape or graph using singular values. Because singular values singular values are non-negative. This is not circle, but something like this. But still, there is some concentrated area, and few large singular value can exist there. If our singular value distribution having this shape, again, which means there are our structure information. So from this singular value and singular vector, we can extract this structure information. But this part is just a random noise part, so we can erase this and we can extract this hidden structure. That is a spectral method. So when we analyze the singular value of this expected matrix and a singular value of this random matrix, roughly we have this result. The spectral norm of random matrix will have this degree, this order, square root of t over mn times n plus n, and the singular values of the expected matrix having this order, t over square root mn. So when the capital T is less than or equal to n plus n, and then the random matrix dominates the expected matrix. Okay.
You're keeping only the values of 1.
Yeah, we're keeping just only the value. Yeah.
But wouldn't it be better to use this information?
So yeah, if we use both information, we can do better. But still, when the capital T, the sampling budget is smaller than n plus n, the negative part also cannot have such a huge singular value, so we cannot extract the hidden structure. So it will be the same. Okay. So to directly use the spectral method, one required condition is T should be much bigger than plus. That comes from our spectral analysis. And this random observations, this uniform random sampling to extract hidden structure is quite wasteful, because all this random sampling just make a regret, because we do not consider any hidden structure. We just randomly give recommendation to a random item. So all this space sampling budget are just a regret. So t much bigger than n plus n is not good sign. So which means this first step already spend more regret compared to our fundamental linear robot. So we have to introduce another trick to overcome such issue. So we use kind of cosine similarity. So cosine similarity is quite often used in many recommendation systems. So cosine similarity is measured to assess the similarity between items. So when item having some observation vector, so the vector consists of response from users. Each item can construct a vector filled with 0 or -1 or 1, depending on the user's response and whether it is already recommended to a user or not. Okay? And from this vector, when we have two items, this is item 1, item 2, maybe the two items will have a different random vector, right? And the cosine similarity is kind of metric by inner product between the history vector. When they belong to the same cluster, more likely the cosine symmetry will be high, because they will share the same preference. Same user will be happy, same user will dislike. Okay. So from the cosine similarity, we can measure the similarity between items. So simply, so this is formal definition, but simply ignoring this denominator, we can construct a similarity matrix by using this. So let's say X is a random adjacency matrix we observe from the recommendation. Then from X transpose X, we can make a similarity matrix. And of course, the diagonal term is similarity by themselves, so that is usually tough. So we build a matrix by X transpose X minus diagonal X transpose X. So erasing all the diagonal term as to be 0, and then use similarity between every pair of items. And also for the proof, we ignore who have positive response more than 3 times. This is just for proof reason, but in practice you can use. We run many simulations, and it turns out it is okay to use just simple X transpose X matrix. But for the proof, we actually ignore users who have response more than 3 times having positive response, because it can introduce some additional correlation between element inside X transpose A. So based on this, the spectral analysis of A matrix becomes more nicer. So the expected matrix of A still have the structure information, because the items belonging to the same cluster will have the same rows and columns. So here the A matrix is symmetric matrix. All the columns and rows comes from the item. And the expected matrix will have such a structure. And again, the X transpose X also a random matrix. Depends on the history. But this is symmetry, of course. And the singular values is, this is m over n0, and this is square root m over n0. So whenever m over n0 is much bigger than 1, essentially, we can observe such singular value distribution. So the singular value of this having this density and few high singular value, and from this singular value and corresponding singular vector, we can extract the hidden structure of items. So this result is much better than the original adjacency matrix, and this is the key part. We can achieve the lower bound performance by our algorithm. So from this step, spectral analysis, we can extract the hidden item structure very accurately using just a 10 times n budget. So constant times the number of user budget, we can extract the hidden item cluster very accurately. And then using the item cluster, we learn kind of Bandit algorithm. So each user independently learn which item cluster is better to himself. Okay? So each user maybe have different preference, but there is only two choice: class 1 item and class 2 item. If there are k clusters, there are only k choices: class 1 item, class 2 item, class k item. So we can design kind of Bandit algorithm. And while learning the Bandit algorithm, in the meantime, we can continuously check the similarity between users. And when there are many similar users to them, we can utilize the side information as well. So the step for Bandit is that each user just independently learn a Merton Bandit. And from the observation, try to cluster users. And from the item cluster and user cluster, estimate hidden parameters. And utilize this hidden parameter to learn this Merton Bandit algorithm. When I explain the row bound, I explain very special Merton Bandit setting, Merton Bandit with given parameters. So when we can extract the hidden parameters from this step, this Merton Bandit is exactly the Merton Bandit with given parameters. So the Merton Bandit problem becomes more easier, and then and our regret bound can be reduced compared to the just pure K-Young Bandit algorithm. So we can achieve very nice regret. And regret per user is just proportional 1/, delta. Without this estimated hidden parameter, there should be some log t here. Every Bandit algorithm without hidden parameter, they always have log t term because of uncertainty of outcomes. But because we can estimate hidden parameters and we use these hidden parameters to learn Merton Bandit here, so we can erase log t term and we can achieve the row bound performance using this 3-step algorithm, 4-step algorithm. And this is numerical example. Basically, because of the initial cold start period, the algorithm performance is not such great. Initial performance behavior is not good, but after sufficiently many iterations, we observed that our algorithm keep the almost same regret, which means our algorithm always recommend the best item to each users. But other existing algorithms just linearly increase because they cannot find hidden items and item cluster and hidden user cluster accurately, even if they learn some kind of roughly millions time of iteration. So this is the result. Okay, so this is the conclusion. So this paper proposed and analyzed several models for online recommendation system with no repetition constraint, and we provide regret row bound and algorithms approaching this limit for all proposed models. Especially model C, I think very interesting, but still we have many assumptions and many strong assumptions, many unrealistic parts. So there are many open directions to relax such a strong assumption and unrealistic part. So that will be our future work. Okay, thank you for attending, and if any questions?
Questions?
Yeah.
So thanks for the talk. I just want to think, I think the most realistic one besides the repeated viewing is users seem to change their taste
Right.
they're recommended. And also the new items come, but that's too complex. But I think in your model, you may also compute the distance across different user clusters. So based on what users being recommended, the user could shift to the nearby clusters in the future. So I think maybe it is possible to also
Right. Very, very great question, and I think that is very fantastic model if we can analyze. So actually, so before this paper, we studied many times many papers for stochastic Blanc model. Stochastic Blanc model is very simple clustering setting with a random graph. Even for the very simple setting, we want to make some time varying scenario. Some membership is time varying, and their connections also appear and go and as time goes by. We want to make very nice and concrete model, and we want to make very nice theoretical result for that case, but still we don't have a result yet. But I very agree that that direction is very fantastic and very interesting.
In our lab, we are solving that complex problem in realistic setting. However, we don't have any technical or theoretical background. So I think this talk may improve my knowledge according to that structure. And maybe we can present somewhat some problems that we are solving in the approach of data mining.
Right. That would be very, very nice.
What about, like, so you had basically it's a bipartite graph,
yeah,
right? What if, to say it's like Facebook and it's more of a general graph, where you could have anyone, like, instead of identifying users and items, you just have nodes in a general graph.
Right.
And you could still have clusters in that setting.
Right.
Like any node in the graph could show up at any time. Like would this analysis extend well? Because like in the adjacency matrix, instead of like items, users,
yeah,
it would just be like users.
Right.
Do you think that would like carry over well?
Yes. So one of my paper considered very similar setting. So this is called stochastic Blanc model. So there are just nodes, and there are some hidden clusters. We don't know which nodes belong to which cluster. And here we can query a pair of nodes at each time. We can ask question whether they exist actually or not. And then the positive response with probability P if the two nodes belong to the same cluster, with probability Q when the two nodes belong to different clusters. And how many samples do we need to correctly classify every item? And what is the best strategy based on past history observation? What is the best next query? And what is the best policy to generate such a query sequence? That is one of my paper, and we have a result for that.
You have this lower bound theorem,
yes,
and maybe I didn't get the essence of the proof. Typically, if I want to prove some lower bound, number of queries, or in this case it's regret, you probably assume that, let's say I have an algorithm, and then if I use this algorithm, I can solve this this other problem by using this, and then since this problem requires something, so this also requires something. It seems like you're showing that if you have an algorithm, you can use that to say that you can deduce the cluster structure from the algorithm. Like, is the idea? The row bound idea was or maybe I misunderstood. Yeah. So in Bandit setting, row bound usually use some hypothesis test. There is one setting, there is another setting. If we can not discriminate this setting and this setting, there's this amount of regret must be appear. And then to identify this hypothesis and this hypothesis, and how many samples do we need to discriminate this and this. Usually the row bound for multi-bandit setting use this proof technique. You prepare two kinds of input structures and then give one of them. Yes.
We have another question from the live chat. What kind of data was used for the model analysis? What kind of data was used for model analysis?
What kind of model data we use for this this analysis is yeah. So for theory, we just use very very constructed mathematical model, and for this also we use synthetic data. So there exists some structure, and we just simulate the random responses. Okay, so there is structure as we assumed in the theory part, and we just run the random realizations, and what really outcome is we present here. Okay.
Any other questions?
What is the definition of regret?
Regret is so assume that there exists some very super powerful algorithm who know everything. Then the system who know everything will recommend the best item all the time. So the regret is the performance difference compared to the best model. So when regret is very small, which means we can achieve almost the best performance the God can achieve.
Letting it accumulate over time.
Yes, accumulate over time. So this flat area means no more regret occur from this time.
Then green line.
Green line is our the conventional techniques. The green line, because the green line cannot extract the hidden structures, the line always increase. But because our model can extract the hidden structure very efficiently, after this part, the regret almost flat.
Usually in any machine learning algorithm, their accuracy converges as training set increases.
Yes.
Then why the green line shows linearly increasing regret? I don't get that point.
So when we learn this simulation more and more, then the green line also can convert saturate some other.
Optimization, instead of recommending just one item, you can recommend like multiple items. And you are trying to maximize the probability of one item that a full one being true. Right. I guess you can extend your framework to that setting. But I guess you can just use the combinatorial problem. Right?
That also very interesting question. Indeed, I'm working on that problem with Professor Kang Mo and his student.
And then the same ideas extended to that setting.
Yes.
You can still keep the kind of spectral analysis part. But the only difference is the amount of data you are doing.
Right. So the analysis is basically the same, I think. I believe. Yeah.
Any other questions? If not, let's take the speaker again.
Thank you.